Jeff. Thank you all for being here. It's a great pleasure. I think the last time I was on this stage was for Rocky Horror Picture Show. And Jeff is also a tough act to follow. So as he said, this wonderful film is about a relationship that goes sour, and the couple chooses to erase the traumatic memory of each other by going to a somewhat shady company to have their memories erased, but things go awry. And so the title of my introduction is, go back please, thank you, Eternal Sunshine with a Chance of Showers, because things can go wrong. So let's go to the next slide. And as many of you know, PTSD, post-traumatic stress disorder, is a big problem, and it and many other mental problems are often due to traumatic memory that elicits emotions, bad feelings, and associated with them, and they plague many people, all of us, to some extent. And getting rid of them, erasing traumatic memory, is a worthy goal in medicine and neuroscience. It would take care of many of these problems if we could get rid of these memories, or so it seems that they would. So is it feasible? Is that something scientifically possible? Next slide, please. So let's look at what we know about, schematically at least, about memory. On the far left, we learn something, some stimulus comes in, and it is stored in short-term memory, and then it can go to consciousness, active memory up at the top, and or it can be consolidated into long-term memory. And once it's stored in long-term memory, at some subsequent point in the future, in consciousness, it can be recalled. The memory can go up, back into consciousness, and we have a memory of the past. And it can be a traumatic memory. It could be a wonderful memory. It could be any kind of memory or mixtures. And it does its thing in consciousness. And when we're done with it for that particular episode, it's restored into memory in a process called reconsolidation. Next slide, please. So memory can be most easily altered during this phase of reconsolidation. We bring it into conscious awareness, and then after we process it in some way, it has an effect on us, but we have an effect on it, and it's restored into long-term memory. And when it's restored, it can be changed. And this reconsolidation phase is the best opportunity to alter memories, to treat and possibly erase traumatic memories. Next slide, please. So, as I said, we want to bring the memory into consciousness, then alter it for reconsolidation into memory. So, if we look at what's happening in the brain with all this, short-term memory is usually conscious and can happen in cortex and prefrontal cortex, and it also goes into a structure called the hippocampus, that little blue worm-like structure up there. And can be, but it's also stored in cortex, all over the brain, all over the cortex, I should say. And an important point is that the strength of the memory, how powerful it is, how long we will remember it, how much we will remember it, how much impact it will have on us, is due to its emotional content. And that is imparted by a little structure called the amygdala, that little pink ball in front of the hippocampus. And the amygdala processes fear and emotion. And if something happens to us and it's a strong emotional impact, we're going to remember it more strongly. It can be good, it could be bad. Your first kiss, or the death of a loved one, or something horrible. Either way, the impact of the memory is charged, and that's due in large part to what happens in the hippocampus. So the stronger the emotion attached to the memory, the longer it's going to be there, the more effect it can have, good or bad, and also the harder it is probably to get rid of. Now, there are amnestic drugs that can wipe out memory, or at least prevent memory storage. They're amnestic from the time that you take them. For example, midazolam, that we use in anesthesia on pretty much a daily basis, gives you about amnesia from the time you give it, maybe a few seconds before, maybe up to 45 seconds before the time it takes to consolidate that memory. Rohypnol, which is the infamous date rape drug, does pretty much the same thing in a more powerful way, and it prevents memory consolidation. But these drugs must be present when memory would be initially formed. You have to have them on board when the memory occurs, or they're not going to do anything. They're not going to do any good. They don't give you significant retrograde amnesia, and they don't discriminate between traumatic, normal, and or positive memories. Ideally, we want to get rid of bad, traumatic memories and keep the good ones. Next slide, please. But during reconsolidation, next slide, please, I see 4 ways to erase memories that are possible or have been tried or are being tried even as we speak. The first is to detach emotional reactions from the traumatic memory with drugs. So this is to say that, well, I'll come back to this in a second. The second is to reassociate the traumatic memory with pleasure, to replace it with something pleasurable. The old switcheroo during reconsolidation. All of these can occur during reconsolidation. 3, to disrupt the specific brain structures encoding traumatic memory. This is what they do in the movie, where they have some kind of brain scan, MRI or something, EEG, and they elicit a particular memory, particular part of the brain lights up, and then they zap that part of the brain. That's not going to work for reasons I'll explain. It's a little naive, because memory isn't stored in any one place. And finally, therapy of some sort and brain stimulation. This can be invasive brain stimulation or non-invasive brain stimulation. Next slide, please. So the first one, as I mentioned, detach the emotional reaction from the traumatic memory itself with drugs. For example, a drug like propranolol, a beta blocker, can block stress symptoms like your heart racing very fast, sweating, dry mouth, all these emotional and the feelings associated with them. These in turn can elicit more mental stress. When you feel your heart racing because of the memory, you get more anxious, more stressed because of that, and it's a vicious cycle. So drugs like this can block the stress response. They don't do anything for the memory, but they take away the affect. They take away the negative stress response and the feelings associated with the stress response. But they don't get rid of the memory. The memory is still there. But they kind of deconditions and it might do some good. But you have to have it on board. You have to have it on board when the memory occurs, or else it's not going to do any good. Next, please. Now, a second is to reassociate the traumatic memory with pleasure or with something better. And I'll give you an example of an experiment that was done in which male mice were conditioned to associate a tone, a sound, a beep, with pain. So they would hear the tone and they would get a foot shock or something like that. They'd feel the tone, foot shock, tone, foot shock. So they learned to fear the tone because they knew what was coming. They were going to get pain. However, next please, they then stopped the pain and kept giving the tone, but paired the tone instead with access to female mice. Next slide, please. Now, I apologize, this is kind of an X-rated slide, and I know this is not that kind of theater, but I think you'll get the picture, literally. Next slide, please. And at that point, the tone was no longer stressful. So because they would associate, the mice would associate the tone with pleasure rather than pain. Next, please. The third is to disrupt specific brain structures encoding traumatic memory. So this is what they did in the movie, or what they'll do in the movie, as you'll see. They would elicit a particular memory and then zap that and get rid of that memory. That doesn't work for reasons we'll see in a second, but it raises the question, where is memory encoded? Where in the brain is memory stored? And I said earlier the hippocampus and the cortex, but that's not the whole story. Next, please. It turns out that specific memories are not stored in any one particular place in the brain. Memory is distributed throughout cortex like a hologram. You know, a hologram projects a three-dimensional image, but if you take the hologram itself, the plate, and smash it into a million pieces and then re-illuminate it with a laser, you don't get a particular bit of information. You see the whole image just kind of fuzzy. The smaller the piece, the fuzzier it is. Everything is stored in every little piece of the hologram. And that's kind of how memory is stored in the brain. A famous experimentalist named Carl Lashley in the early part of the 20th century taught ingrained memory in animals and then eradicated various parts of the brain. And he wound up basically eradicating the entire brain and never got rid of the memory, almost the entire brain. It was everywhere. And he concluded that memory was impossible as kind of a facetious joke, because obviously it is. But Carl Pribram, another Carl, and a very famous neuroscientist, described it as a hologram because it's exactly how a hologram is stored. So it seems that memory is stored throughout the brain like a hologram. Now, at the cellular level, memory is presumed to be encoded in the strength of synapses. And this is called synaptic plasticity, Hebbian synapses, and so forth. It's based on the idea that the brain is a computer. Next slide, please. So this is the metaphor or the analogy that dominates neuroscience and AI and philosophy, that the brain is a computer, that neurons, and we see a bunch of neurons on the left, they're connected by connections called synapses, and they're likened to a network in a computer, as you see on the right, with nodes, the spheres, that have connections whose strengths can vary. They can be strong or weak. And depending on the strength of particular connections here, information flowing through this network is going to be channeled in particular pathways. And you're going to wind up with particular patterns coming out on the other side, depending on the strength of the synapses. So by adjusting the strength of synapses for a given input, you're going to get a given output. And this is how learning is thought to occur in the computer brain analogy. Next, please. And if we look at an actual synapse close up, we see a neuron at the top, an axon bringing an electrical impulse down to another neuron where we see blown up here and releases vesicles which travel across the synapse and bind to receptors. And the party line, the understanding in neuroscience and philosophy and AI is that memory is stored in the synapse. However, these receptors only last hours to days, and yet memories can last lifetimes. So this is obviously not the whole story. Next, please. If we look more closely at synapses, a more modern view, most memory, or most synapses that deal with memory, for example, NMDA receptors with glutamate receptors, are on these outpouchings called spines. If you see at the very top, the yellow outpouchings are dendritic spines on a dendrite. And the far left, we see what they look like without the membrane associated. And if we look inside them in this picture, we can see the receptors on the top, the glutamate receptors, which again are only there for hours to days, and yet memories can last lifetimes. And the structure of the spine is made up of actin, a cytoskeletal protein called actin. And here we see another cytoskeletal structure called microtubules that come into the dendritic spine. And memory must be stored at a deeper level than the receptors, possibly in the spines, in the actin, or in the microtubules. Next, please. So it turns out that if you disrupt actin by disassembling the actin, you can reduce cravings, for example, in methamphetamine addicted mice. People have done this experiment, and they get the mice addicted, and they give them a clue that they're going to get what they want. And if you block that, you can block that by destroying the actin in these synapses. That seems to work. It's not a very practical solution for us because it'd be very destructive, and it doesn't really isolate one synapse, one versus another. So here's another view of the synapse where we see the actin up there, and there's another player here called CAMK2 in the hexagons, which associate with the microtubules. And next slide, please. Another way to disrupt memory is by destroying this or disrupting this enzyme CAMK2, which blocks memory during reconsolidation. CAMK2 is one of my favorite enzymes. Sounds kind of nerdy to say that, but I'll explain why. And you can see that it's associated in the spines, and it also associates with these structures called microtubules. So, and that I think is the key, and you can see on the far left where that occurs in a neuron. Next, please. So here's a microtubule, which is my favorite structure. Many people who know me know that I've been obsessed by microtubules for almost 50 years now. And they're inside neurons, and they do many things, including acting as kind of a track for these motor proteins to move cargo along the dendrite or the inside the neuron to deliver them to a particular synapse for strengthening synapse for learning and memory. And tau protein acts as a traffic signal for these. Now, tau and microtubules are famous for something else. Next slide, please. Because inside neurons, they can be damaged, and when they are disrupted, they result in Alzheimer's disease. Now, we know in Alzheimer's disease, we have these amyloid plaques on the outside, but the real cause of the cognitive dysfunction and memory loss is what's happening inside the neuron when the microtubules fall apart. So they're very, very important. Next slide, please. So what happens in a synapse is calcium comes in and activates this CAMK2, and it then binds to microtubules. Next slide, please. So CAMK2, as I said, is my favorite enzyme. And on the far left, you'll see an inactivated CAMK2. It's a snowflake-shaped molecule. And when it's activated, when calcium comes into the neuron, it sends out these kinase domains, kind of like arms and legs that look like, well, arms or legs, or somebody calls it a poodle, a nanopoodle, because it's nanoscale size. And it can phosphorylate, these are the phosphorylation sites, to encode things inside the neuron. So what might these encode inside the neurons? Next slide, please. Well, my colleagues and I looked at this and said, we wonder if they're binding to microtubules. And at the top in the gray, you see the lattice structure of microtubules. And at the bottom, you see that sure enough, the CAMK2 matches up perfectly with the hexagonal lattice enzyme and size and geometry of the microtubule lattice. Next slide, please. And as we showed in a publication, the nanopoodle can land on the microtubule and exactly fit on this lattice structure, and by phosphorylation, leave a memory trace behind. Next slide, please. So here's the idea. The nanopoodle lands on a microtubule, kind of like the moon lander, I think, but at a nanoscale. And if all four kinase domains phosphorylate, you get six bits of information. And so the amount of information, there's hundreds of these per synaptic event and thousands of locations for them. Next slide, please. So the amount of information that can be stored in a microtubule in a neuron or in many neurons is enormous. And this is a paper we published suggesting that this is where memory is stored. These are fairly stable. They don't have the problems that synapses do. Next, please. So just more about microtubule processing information. I happen to think that they are where consciousness occurs and where memory occurs, but that's a whole other story. Next slide, please. I will say, however, that due to these studies, this is rather technical, but Anirban Bandyapaty's group showed with some very elegant nanotechnology studies that the microtubules have vibrational resonances and over a very wide range of frequencies from terahertz, which is visible light, gigahertz, megahertz, kilohertz, all the way to hertz, EEG. And so they're resonators, they're vibrating inside neurons. And I think that's the key because, as I'll come to in a second, I don't think the brain works as a computer. I think it's more like an orchestra. And I think consciousness is more like music than it is a computation. And the microtubules are probably the instruments of the orchestra. Next, please. So this is shown in this slide where we start on the far left with a neuron, a pyramidal cell neuron, and look inside and see the microtubule and see these dipole oscillations. And we go all the way down to these pi resonance oscillations, which is where anesthesia works. And we study anesthesia, and it turns out that anesthesia appears to dampen these terahertz vibrations in microtubules. Next slide, please. So let's get to the last category, therapy and brain stimulation, and how this may occur. Next, please. The most famous one is the neuralizer. I'm sure you've seen this. It's a great movie, just watched it recently, where they erase people's memory by this flashy thing. And there's also, on a serious note, some weaponry developed by the Russians. We hear about these sound weapons and electromagnetic weapons. Something like this may be possible. Not necessarily the neuralizer, but something like that. Next, please. Now, there's some other things that are used today. Transcranial magnetic stimulation, TMS, that imparts a magnetic signal to the brain and kind of stuns the brain. Next, please. Transcranial direct current stimulation, TDCS, where you put electrodes over two parts of the brain. The problem with that is that the current goes along the surface of the cortex, not through the brain. Next, please. And also transcranial ultrasound, TUS. And that's me, and that quite literally is my brain on ultrasound on the right. And it imparts mechanical vibrations in megahertz, which turns out to be the vibrational frequency of microtubules. And it gives you a very, very pleasant feeling. And we're actually doing some research with that to treat things like Alzheimer's and chronic pain and so forth. And finally, UA psychologist Jay Sanguinetti who's here working with mindfulness meditator Shinzin Yang, find that focused ultrasound can detach consciousness from the brain's default mode network, resulting in a state of Buddhist-like detachment. And that might be something useful for traumatic memories, separating the suffering from the pain. You might have the pain in a chronic pain situation, but don't need the suffering. You can have the memory without the trauma associated with it, and it won't have the effect on you. Next, please. And one final point, this is the multiscale hierarchy I mentioned earlier. What happens if you go this way, if you go faster and smaller down into the quantum world? Next, please. And some of us think that that actually connects to the fine scale structure of the universe, shown on the far right in the space-time curvatures, which would be smaller than biology, faster than biology, and not necessarily need the biology to maintain information. Next, please. Which could account for things like out-of-body experiences and so forth. Now, I get a lot of flack from my neuroscience colleagues and say, how can you even talk about that? There's no scientific explanation. Well, what I just showed you could be a scientific explanation. And what I say to them is, if you can't explain consciousness in the brain, you can't tell me that it can't exist out of the brain. So I think it's a possibility, and there is a scientific explanation for it. So here is the, again, what I just showed you. And finally, the last slide, I think, is this. Oh, go back. Yeah. I wrote this article a few years ago about the idea that consciousness is music and the mind the brain is more like a computer, and that to treat mental and cognitive disorders, we should treat it more like music and change the music. And I used a quote from the Beatles' Hey Jude, take a sad song and make it better. And after 40 years of studying consciousness, I do believe that consciousness is more like music. It's music in the structure of the universe that percolates up to our brains, through our microtubules, to our mental states that we have. And so I hope your mental states will enjoy the movie. I love this movie. It's a kick every time I see it. And have a great evening. Thank you very much. I'm going to take some questions.
So we have time for a couple of questions. Tom, do you want to turn the overheads on, the lights? Yeah, so I have this microphone, so does anyone have a question down here in this part of the theater for Dr. Hameroff? Yes, please, sir.
That 10 to the minus 34 or 37 sounds like the Planck constant.
Yes.
And,
I don't see who's talking.
yeah,
Okay.
it sounds like the Planck constant,
Yes.
which is the smallest of smallest of smallest, the units maybe that God himself uses, if you want to use that metaphor. 10 to the minus 37, which is Planck's constant.
Right. It's kind of the basement of the structure of the universe that everything comes up for. And so you might say, well, if it's that small and that tiny, how is it going to have an effect at these large scales? And I think because these patterns resonate and interfere upwards in size and slower in frequency through the once you get into the brain anyway, terahertz, gigahertz, megahertz, and kilohertz, and then EEG. In fact, some of us think that EEG, which is used commonly, is actually an interference pattern of like beat frequencies, like in music. You know, if you have two instruments, like two guitars that are slightly out of tune, the difference between their frequency will give you a beat, and it's much, much slower. And we think that EEG, which is in hertz, under 100 hertz, is actually a beat frequency of much faster megahertz or gigahertz vibrations in microtubules. But you're right about the Planck scale. That's intentional.
Thank you.
Any other questions? How about up here? Yeah.
What affects the accuracy of memories? Often two people will experience the same thing and remember it very differently.
Yeah, very good question, and that's true. And in fact, sometimes we have different versions of our own memory. You go back and revisit it, and it could be through this reconsolidation phase, because every memory that's stored is influenced by the context in which it is stored and what is happening to the individual when it occurs. So two people are going to have different contexts of it and different perceptions, not to mention political differences and all that. So we're going to have content and context differences among people, and also in the same person at different times on reviewing the memory. And in fact, that's the hope of altering memory, that we can change it in a way that takes away the negative affect and makes it more pleasurable.
Any other questions? Let me just get this right up here. I think you had your hand up first. Right there in the middle.
So I believe that there are alpha and beta proteins throughout the body, like microtubules.
Oh, yeah.
Could this suggest that there's memory and consciousness throughout the whole body besides the brain?
It could. Memory and consciousness is a little bit different. For consciousness, you need a certain number of them to be quantum entangled closely. But for memory, it's not quite as rigid. And in fact, for example, there are reports of people who have heart transplants get memory from the donor. And there are nerve ganglia in the heart with lots of microtubules. And some people think there's consciousness in the heart. But whether that's true or not, there certainly can be memory. And there's some evidence for that in the transplant literature.
Yeah, we had a question right here.
Yes, I wondered what your thoughts are on eye movement desensitization and reprocessing. I had it done for myself. I used to be an EMDR therapist as well, but I went through a lot of trauma. And after I had extensive EMDR, it removed the emotional connection. I still have the memory, but it doesn't matter. And so, and it stimulates both halves of your brain. Do you have any thoughts on that modality of?
I don't know much about it. I've heard of it.
Okay.
I've heard good things about it. I assume that the treatment, the therapy was during the reconsolidation phase, or was it? Was the memory elicited and then the EMDR was done at that time? So it would be fall into the same paradigm. So there are many different types of therapies, meditation, psychotherapy, right. Freudian, Jungian, whatever, that can be done on the memory once it's brought into consciousness in the reconsolidation phase. So when it goes back into memory, it's altered.
Right. Okay. Thank you.
We have time for a couple more questions. There's one down here. Right here.
Thank you. That was excellent. Have you considered applying the microtubules concept to artificial intelligence, and how successful has it been so far?
They don't like us. We've been fighting artificial intelligence. I work with Roger Penrose, and this all started when he wrote a book called The Emperor's New Mind, which attacked the idea that artificial intelligence or computers could be conscious. They're algorithmic, and there's no room for free will or things like that. And they're based on the idea that the brain is a computer, and I disagree with that. Now, I've tried to tell them that things like deep learning might be analogous to processing inside neurons and so forth, but they're pretty wedded to the idea that the brain is a computer, and you need an algorithm, and that you need switches like synapses to that's why they like the synapse idea, because it's analogous to the computer idea. So I've thought about it. I think they'd have to modify things. For example, you could make artificial microtubules with technology like fullerenes, buckyballs and fullerenes and graphene, things like that would have the quantum effects that we want. So I think it's possible, but in silicon, I doubt it. I have friends who work in quantum computing at Google, for example, and they're starting to worry that their quantum computers might become conscious, and that would be a public relations and ethical dilemma for them, because they don't want it, and they're not ready for it. But conventional AI through silicon and algorithmic processing, I'm very skeptical of it, and because for the reasons I said. So I doubt it.
All right, so I feel like we need to explore the consciousness of the front of the theater. So we have time for two more questions. So how
There's
about
two up here. They've been very patient.
This gentleman seems like he's been very patient.
Not as patient as her, but go ahead.
So, how do you think memory influences our own personal concept of free will, the simple motor movements and more complex decisions that we make from day to day?
Well, memory is important why we're going to choose to do a certain thing, but there's a bigger problem with free will if you follow the computer idea. Because if you say something and I answer back to you immediately, if you look in my brain to process what you said, that activity happens after I've already answered you. And because of that, AI and neuroscience and philosophers say, well, you see, that just shows that there's no free will, that we're responding. I'm responding to you non-consciously. My autopilot, my unconscious autopilot is responding. But if it's a quantum effect, I didn't really talk about quantum mechanics. You can have temporal symmetry, and you can have what would appear as backward time effects. And there's actually pretty good evidence from this, going back to Ben Libet and Daryl Bem and many, many other things. And that's perfectly okay in quantum physics. So I think with quantum physics, you at least solve the problem of responding in real time. And until you solve that, free will is impossible. And so it's impossible according to the AI brain as computer approach. With the quantum approach, it does become possible. And I've written about that, and Roger Penrose and I have written about that. And so that's what we think about it.
I was just curious about the propranolol, actually. You mentioned that it could be applied while memory is being manipulated in active memory to reduce the stressful effects of a memory in terms of like sweating and nervous behaviors. How many rounds would that take to kick in naturally when the memory is evoked?
Right. I don't know exactly, but it would. What it does, as you said, is take away the visceral and somatic response to the memory. So something happened, you remember something, and it makes you feel really bad and icky, and so you start to sweat, your heart starts to pound, have palpitations, and so forth and so on. That you can block, but you still have the memory. So if you do it again, you kind of desensitize. So it's kind of separating the affect, the response, from the memory, but the response itself causes stress. So, but you'd have to have it on board when that memory occurs. So I don't know if people are still using it or not. They may be, but it's not the ultimate solution.
So you would have to use the drug every time that
Yes.
you had the memory.
Yes, and propranolol has a lot of side effects, for example.
I think it's time now that we watch Jim Carrey and Kate Winslet get their brains wiped. Yeah. So
Can I just say, I met Jim Carrey once at a conference with Deepak Chopra. He's a really cool guy. I tried to get in touch with him about this, but I couldn't reach him. He's got his own art career now.
he's a busy guy. But I want to thank you, Dr. Stuart Hameroff, for taking time to be here tonight. Thanks everybody for coming. Enjoy the movie.